What is going on? Pre-calculus. Hope you're all having a fantastic day today. It's a beautiful day outside. The sun is shining. The birds are chirping. Or the thunder could be rolling. Either way, it doesn't really matter much. Today we have a fantastic day. Fantastic little lesson planned out here. We're going to be talking about the graphs of trigonometric functions. This can get a little hairy, and it's a little bit long already. So let's jump straight into it. We're going to be graphing sine x. So graph the function f of x equals sine x, with x as the independent, meaning it's on the x-axis, obviously, and sine x is the dependent, meaning the y's. X can represent an angle or a real number. So very simple here. We're just going to complete the table. So I can use my unit circle for this. The sine of 0 is 0. The sine of pi over 6 is 1/2. Sine of pi over 2 is 1. And for the sake of time, I'm just going to power through these real quick. It's 1/2, 0, negative 1/2. We're not going to go over this because you already know how to find sine values from your unit circle. This should all be old hat. Old hat. Negative 1, negative 1/2. Now notice we're on the negative portion of this now. So it looks like we're going from negative 2 pi up this direction to 2 pi. Negative pi is 0, 1/2, 1/2, and 0. Yay! Okay, so very easy idea here. Plot those points on this graph. All right, so starting with 0, 0, and I'm going to go kind of quick here. Pi over 6, 1/2. Pi over 2, 1. Oh, excuse me. I'll draw that on pi over 3. So pi over 2, 1. 5 pi over 6, 1/2. Pi is 0. 7 pi over 6, negative 1/2. 3 pi over 2, negative 1. 11 pi over 6, negative 1/2. 2 pi, 0. And so that should look somewhat familiar. That's the sine wave, isn't it? And then we can go the other direction as well. So this will be negative pi over 6. Each one of these intervals are pi over 6 units. It says so right here. So this will be negative pi over 6, negative pi over 2, 1, negative 1 rather. Negative 5 pi over 6, negative pi. And you'll notice that there is a format to how this thing works. And draw a smooth continuous curve. So starting anywhere really. Smooth and continuous. If I was ever a radio DJ, that would be my name. You're listening to Smooth and Continuous Jazz right here on 91.3. Simply beautiful. Put me in, give me a job. All right. So that's called the sine wave. Now you've probably heard about the sine wave a couple of times. If you're in physics. If you're in physics, you've probably seen the sine wave already. If not, hey, there's no worries. Here's your sine wave. It's pretty, isn't it? Now, I actually detached this page, but I'm going to go to the next page. And I'm going to show you how to do this with a calculator. So I'm going to have my calculator handy. If you want to pause it real quick, get your calculator, you can. So I've got my calculator. I'm going to make sure it's in radians mode, which it is. And then I'm going to set my window, go to window. Oh, no, wait, y equals, sorry. I'm getting so excited. Sine x, just like that. Pause if you need to. Go to your window, and I'm going to change my x min to negative 2 second pi, and my x max to, oops, not negative, but 2 pi. My x scale is going to be pi over 2. And that's just a general rule that I like because with the x scale, what it does is it breaks up your x-axis into increments of pi over 2. Instead of going up by the little tick marks being 1, 2, 3, 4, 5, it's pi over 2, pi, 3 pi over 2, 2 pi, that kind of thing. Y min, negative 2. Y max, 2. Why? Because I know from my sine wave it's not going to be any taller than 1, so there's really no point in going up to 10. And then graph. Look at it. It's beautiful. It also looks exactly like what I graphed. Oh, yeah. Anyway, Press graph, check your graph on the calculator. Now change your window from -4 to 4. So -4 pi to 4 pi. So window -4 pi to 4 pi. X min, X max, graph, and look at what it does. It keeps going. Kind of like a sound wave. It keeps on going. Fantastic. So let's look at some questions it's going to ask us about this graph. What does the graph look like for x is greater than 2 pi? So out here at 4 pi, what was it doing? Well, here's 2 pi. So what did it keep doing? Well, it kept repeating, right? So it repeats the pattern. Repeats the pattern. Starting at x equals 0, the graph completes one complete cycle at x equals 2 pi. Here's what this means. Big points, important points. One cycle is from this point to this point, or from a crest, which is what we call the high point, to a crest, or a trough, the low point, to a trough. Think about it. A horse drinks out of a trough. If you fill this up with water, a horse can drink out of it. Yay, horsey! Crest, trough. You can either measure this, -3 pi to pi over 2, -3 over 2 pi rather, -3 halves to +1 half, that's 2 pi in units, or from where it crosses the x-axis on an uphill to where it crosses the x-axis on an uphill, 0 to 2 pi. We call that the period. The period is how often it repeats, right? The period is the length of one complete cycle. So reset your window from -2 to 2. So I'm going to come over here, window, -2 pi to 2 pi. And then graph, it wants to know what is the maximum value of f of x. Well, what was the highest point it ever reached? Well, your highest value was 1. Never goes any higher than that. And where does it hit? Where does it hit them at? Where is it hitting its maximum values? Well, for this window specifically, it happens here. This is -1, -2, -3 pi over 2. That's why we broke up that x-axis like that. -3 pi over 2. And this is x equals these guys. And +pi over 2. Yay! The minimum value here is -1. And where does it happen? It reaches its negative at -pi over 2 and +3 pi over 2. What's the domain of the sine wave? Well, the domain of the sine wave is all real numbers, right? Or -infinity to infinity. It goes on forever. Forever and ever, never, never, never. But the range is limited from here to here. The range is limited from -1 to 1. And it's touching here, touching here. Where are the x-intercepts just on this part of it? Just on this part, where are your x-intercepts? Well, if you look on here, it happens at -2 pi. -2 pi. This is -pi over 2, or no, I'm sorry, -pi here. 0, pi, and 2 pi. Okay. Where are the y-intercepts? Well, that's at 0, 0. And then sine x, even or odd? Well, if I look at this function, it has a y-axis of symmetry, or no, excuse me, I'm sorry. It has an origin symmetry. This point, if I make pi over 2 comma 1, negative pi over 2, -1. See how it's an origin symmetry? The other way we said is if we flip that upside down, we get the same graph. It's like magic. So it is odd. All right. So again, what that means is the whole f of -x equals -f of x. Remember that from the very first unit in the year? Oh yeah, we remember it. So what that means is that if you had like sine of pi over 6, it's going to be the same thing as negative sine of pi over 6. For example. Okay, let's keep going because this is starting to get a little long. Okay, same thing here, but now we're on cosine. Okay, cosine, so what I'm going to do is the exact same thing actually. So if I plug a 0 in for cosine, I get 1. Plug in a pi over 3, I get 1/2. These are just the nice ones. It's not very nice to do cosine of pi over 6 because it's the square root of 3 over 2. Ugh, that's an ugly number. Pi over 2 is 0. Just filling this in real quick. Negative 1/2, negative 1, negative 1/2, 0, 1/2, 1, 1/2, 0, negative 1/2, negative 1, negative 1/2, 0, 1/2, 1. Okay, cool. I have the sniffles. Oh, the sniffles. And let's plot that. Now, the major thing I want you to get here out of this whole lesson, if you just get this, then I'll be happy. Okay? Sine wave starts at 0, 0. The cosine wave looks exactly like it, but it starts at 0, 1. From this point right here, 0, 1. So plot those points. 0, 1. I'm going to plot all of these here for you. It's having a pi over 3, 1/2, 0, negative 1/2, negative 1. Here, 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 1. Fantastic. Moving on. Here, 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 here. Yay! Nice and smooth. That's really going to freak out the people who watch these on twice the speed because that's going to sound normal. It's going to be nice and smooth. Anyway, you get the idea. Okay, so look at the difference between the two. Let me get them both on screen here for a second. Okay, so the top one is the sine wave. Same structure, same wave actually, but it starts at 0, 0 and goes up. This one starts at 0, 1 and goes down. Sine wave, cosine wave. So a lot of these on the next page are going to be very similar, and you can graph this. Cosine x, graph. There you go. Right? Using the same window, blah blah blah. Okay, so it says the graph of cosine x is periodic. The period is how long it takes to complete one full cycle. Well, if I look at my graph here, remember one full cycle is from 0 uphill to 0 uphill, or from crest to crest, or trough to trough. It's all the same distance, so from one point to the same point on the next wave. So top of the wave to top of the wave, from 0 to 2 pi, so that means my period is 2 pi. Yay, the maximums are 1, and they happen at negative 2 pi, happen at 0, and they happen at pi again. The minimum is negative 1, and it happens at negative pi and pi. Domain is all real numbers, negative infinity to infinity. Range is negative 1 to 1. Because it's the same wave as sine, just scoot it over a little bit. X-intercepts happen at negative 3 pi over 2. I'm just looking at the graph and coming up with these as I go. Negative pi over 2, hopefully y'all can see those. Pi over 2 on your own graph, and 3 pi over 2. Your y-intercept is 0, 1. That's the big guy. That's the important one. And you see how this is even or odd? So this is a y-axis of symmetry. That makes it odd. No, even. Chunk, I am so backwards today. Take a moment. Breathe. The graph of f of x equals sine x and f of x cosine x are called sinusoidal functions because that's this, right? Remember, quadratic is x squared. The parabola is the shape. Sine is the function. Sinusoidal is the shape. Sinusoidal is the shape of sine and cosine. This guy, on the other hand, oh my gosh. Tangent. See if I can get this done in the next 5 minutes. What's the tangent of 0? 0. What's the tangent of pi over 4? 1. What's the tangent of pi over 2? Whoa, Mr. Ballard, hang on a second. Pi over 2 on my unit circle was up here at the point 0, 1. Y over x is 1 over 0. That makes this undefined. Oh my gosh. This would be -1, 0, 1, undefined. -1, 0, -1, undefined. 1, 0, -1, undefined. 1, 0. Tangent. Let's read very carefully number 2. From f of x equals tangent x. From your table on the grid below, recall an undefined value will produce a vertical asymptote. Now that's from a little bit of algebra 2 there for you. Undefined, remember undefined means a slope that is undefined. It's vertical, right? This is undefined slope. Horizontal slope is 0. So undefined. So anytime you see undefined, it's a vertical asymptote. Draw the vertical asymptotes as dashed lines. Let's do that first. I'm undefined at pi over 2, so I'm going to go to pi over 2 right here, and I'm going to draw a dashed line straight up. Like what? Pi over 2, like what? Let's see what I can do. Next one, 3 pi over 2. Like what? Dashed line straight up and down, son. Vertical asymptotes. You know what's special about them asymptotes? You can't touch. You can look, but you can't touch that asymptote. -pi over 2 and -3 pi over 2. That's how I remember it anyway. Don't touch the asymptote. All right, and then if I plot 0, 0, my first point there, and then pi over 4, which is actually what, here-ish, between pi over 3 and pi over 6, pi over 4, 1. Ooh, gross. Okay, and then 3 pi over 4, which is between 2 pi over 3 and 5 pi over 6. If you look at your unit circle, -1, 0, 1. Oh, wait, no, I'm sorry. I'm getting all mixed up. -1 here. And then pi is 0. I put the 0 in the wrong place. That's what I did. 1 here. In between, it's 1.5 dashes away from pi. And then -1 here, 0 at 2 pi. Okay, and then come on the other side. So the pi over 4s are in between your values. That's the only thing that's weird about these. If you start at pi is 0, -pi is 0. So if you start down here at 0, go 1.5 over and go up to 1. Go 1.5 over, go down to 1. That's how I remember it anyways. Your next 0 is -2 pi. So 1.5 over, go up to 1. And then we're off the grid. So I'm going to stop there. Draw the curves toward the vertical asymptotes. Vertical asymptotes are kind of like black holes, right? That means someone divided by 0 and everything went to poop, and then you kind of gravitate towards them. Like black holes, they pull you and they suck you in. So here's what it looks like. Remember, asymptotes I approach, but I never actually touch. That's a little bit better. And then straight down. And I'm actually going to stop at 2 pi and not do the right side because I'm off my graph. I'm off my rocker. Ha, 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 ha. And then the right side here. Tangent is a weird dude. Let's graph him on the calculator. If you need to pause that, pause that. But for the sake of time, let's graph him on the calculator and see what happens. Tangent of x. Whoa. That's what I have. It's pretty cool, isn't it? Okay. And then I'm going to go over here. On your calculator, change your y min to -4 and for it. I'm going to let you do that. The period is how long it takes to complete one cycle. So if you look right here, my period, this is one full cycle right here between asymptote and asymptote. So from -pi/2 to pi/2, well that's 1 pi, right? -1/2 to 1/2, that's a full pi. Or each of these spaces are pi/6, so that's 1, 2, 3, 4, 5, 6 pi/6. So the period is pi. The vertical asymptotes on this graph specifically happen at -3 pi/2. And you know they go on forever, but this is just for this graph specifically. -pi/2, pi/2, and 3 pi/2. Domain, now your domain here, domain is going to be a little weird for pi because if you look at what is happening, hang on. If you look at what's happening with tangent, I'm sorry, I had a brain fart there for a second. If you look at what is happening for tangent, we have a value at every pi/2 that gives us an asymptote. Every odd pi/2. So what I'm going to say is x can't be pi/2. It also can't be 3 pi/2. And if I kept going, it wouldn't be 5 pi/2, 7 pi/2, 9 pi/2, 11 pi/2, all the pi/2, all the odd pi/2. So what I'm going to say is x cannot be odd multiples. And this is kind of a weird idea, but odd multiples of pi/2. See that? So 1 pi/2, 3 pi/2, 5 pi/2, 7 pi/2, all the odd numbers pi/2, you can't have those. But your range, oh, now the range goes up here to infinity, down here to -infinity. So the range is all real numbers. X-intercepts happen at -2 pi, specifically on this one. -2 pi. What's the next one? -pi, 0, pi, and 2 pi. Your y-intercept happens at 0, 0. And tangent, even or odd. Even or odd. Now an odd means that if I flip this upside down, I get what I started with. Looks like it to me. 0, 0 up on the right, down on the left. 0, 0 up on the right, down on the left, and it goes through the same points? Yeah. So it's odd. Okay. This was admittedly a very crash type of course on everything involving sine, cosine, and tangent. Just remember that this was not meant to be an all-inclusive, get you to understand everything. This is just meant for me to get the notes out of the way so that we can get to class and I can actually break this junk down. See it!